A person with long-sightedness, if not hypermetropia, can see far-off objects but not the near ones. So the image of a near object is formed behind the retina of the eye, that is the issue, and the near point is obviously greater than 25 centimeter. Okay, the thing is, see, the person can see very far off objects, not an issue, but instead of being 25 centimeters, this person, more than 25. It can be any value more than 25. So from here till infinity, the person can see. So this space is visible for this person. Is visible. If this is actual 25 centimeter, right? So the any object over here to this person, to the hypermetropic person, the light will converge behind the retina. Okay, I mean, obviously not physically. Right? So it appears to form behind the retina. This is the issue. So this is the nearest the person can see. Near point. So what is the cause of this? Increase in focal length of the human eye lens. So this lens, the focal length can increase, or size of the eyeball becomes too small. So these are the issues. How can we correct it? The correction happens with the help of convex lens. So how does it do it? That you will understand in the ray diagram. So we'll see this practically. A scenario wherein the person is suffering from hypermetropia. So we have the retina and the lens. So this lens can form the image behind the retina. So we see a sharp image. Now, but the actual space position of the retina is that itself. So with a suitable convex lens placed in front of the eye, you can see a clear image. So that's how we can correct it. Again, the image is there, but it's formed behind the retina. To correct it, if you use convex lens, right, we will be able to see, or the person who has hypermetropia can see it clearly. So how does this happen? Quite simple. The nearest point of a hypermetropic person will be obviously more than 25 centimeter. So say this is 25 centimeter. So this is what will happen. So anything beyond this point, the person can see. From here till infinity, this is visible for this person. So if I happen to keep an object over here, exactly over there, okay, not that, let me use some other color. So what will happen? It will converge. Right? It will converge onto the retina. But anywhere between this, what will happen? It will appear to form behind the retina. Something like this. To correct this, we will use convex lens. Okay, I'm not able to draw it. Now, so let's keep the object over here itself. I'll just take a dot. That's easier to draw. So the lens, through the lens, this will happen. And what will this do? See, this is a convex lens. So what will it do? It will try to converge. That is, it will try to make it a bit parallel. So I can draw it a bit up only. So it will try to bend it, make it a bit more parallel. And this is how it looks. So if we trace back this ray, if we trace back after the lens has converged, right? Not lens, sorry, the ray has converged. If we trace back this, can you see that? So this will be the position of the image. Again, this is a convex lens, and the image of the lens, convex lens, is over here, and this is the new object. New object for what? New object for the eye. So this person, he or she, now will be able to see this. Why? Because it's in a place, this space, okay, wherein the person can see. So this lens will create such an image. Okay, so this is your correction. Right? So this is how we can correct a person with hypermetropia. Again, the same logic. So get the object in a space, or the image of the object in a space wherein the person can see, and the person will be able to see. As simple as that. Right? So please pause and please write it off. This is your near point. And now you guys can have a look at the experiment again.